Are we rolling?
Yeah, the button turned bigger, so.
Perfect. All right, good job, bro. Talking about dilutions or dilutions. I'm going to go quick through this because it's not a huge thing, but I have to give you at least one example in the notes. And I'm going to show you how to make one up here. So we'll use an example, and then I'll show you how to do it. Back of your reference tables has the formula for this, sort of. Go ahead, go to the back of the reference table, please. I say sort of because that word isn't written anywhere on the back. There's an equation or a formula that we use for two different things. So let's see if you can find the one on the back that looks like the one I'm writing on the board. Write that in your notes and then find it on the back. Tell me which equation on the back looks most like that. Monique. Titration, right. MA times VA equals MB times VB, which is acid-base chemistry stuff. You will learn that in a couple months. This equation is literally the same, but instead of A and B, which is acid-base, we use 1 and 2. What is 1 and 2? This is called, sort of, we'll just for the sake of the demonstration, and you don't know any different, we're going to call this a stock solution. What's a stock solution? It's the one I keep in the stock room, the back room that is like the full concentration. So this is very concentrated. Okay, notice the color, how dark this is. Very concentrated. It's a solution of potassium permanganate, has a high molarity. I didn't calculate it, but the molarity is probably like, we'll just throw a number on it, 20. Okay, molarity of 20. So I put a lot of the powder in here. It's like a purple powder. So this is potassium permanganate. This is called a stock solution. This would be number 1. Number 2 is what we're going to make. This is going to be the number 2. This is going to be our diluted solution. So what we're going to do is we're going to take a little bit of this, put it in here, and then fill up, I don't know if anyone you can see, there's a line here. We're going to fill it up to the line with water. Then what that means is you have 250 milliliters. So this is measured precisely, accurately, is a better word, for 250 milliliters. It's called a volumetric flask. It's very useful. I don't have to mess around with graduated cylinders and all that jazz. I know when I fill it up to that line, that's exactly 250. So I'll take a little bit of this and then a bunch of water, mostly water, fill it up, kind of shake it up a little bit, and I will have a dilution, a diluted solution. So I take what's concentrated, add a bunch of water to it, and it becomes diluted. So that's what a dilution is. You should just have a concept, if you take chemistry, of what that means and how to do it. So what I'm going to do is use this example. We'll kind of do it together on the board using the equation, and then we'll do it up here just so you can have a visual of what it looks like. All right, so you're trying to make the solution weaker. That's what you're trying to do. But I want to say one more thing. M times V. What does that equal? Look at the molarity formula. What's M times V equal? So molarity times volume. Because M is molarity and V is volume. What is M times volume, right? Or molarity times volume equal? If you look at that molarity formula. How about here? If you look at the molarity here, I'll write it down. We have molarity equals moles over liters. So what happens when you multiply the molarity times the volume in this equation?
It will equal the moles.
It will equal the moles, right? So molarity times liters equals moles. So I want to make something real clear with dilutions. Put a little star here. The moles do not change. What are moles? It's the number of particles. That's all moles are, right? Moles is a measurement of the number of particles. That big number, 6.02 times 10 to the 23rd. So whatever we find here, so if I multiply the molarity by the volume, and by the way, this is 100 milliliters. It's just a smaller version of that. So if I take the molarity and multiply it by the volume, I can figure out how many moles of the potassium permanganate I have in here. That number won't change in the diluted. So when I dilute it and make more, right, more water, it's a larger volume, what happens is the molarity goes down. So these two change proportionally with those two. So if I get half a mole here, that equals half a mole here. I really want you guys to understand that the number of moles that are dissolved doesn't change. It because the volume changes proportionally, right? Less volume, more volume. Higher molarity, lower molarity. So they both change proportionally. That's why this equals this. So it's not a huge thing if you're not completely following me. I just want you to understand the moles do not change. And that's kind of where this comes from. So I'm going to write down a sample problem using this, and then we'll do it, and then that's it. We're going to move on from dilutions and hopefully start something new. All right, so here we go. How many milliliters of a, again, we'll make up a molarity, of a 20 molar stock solution. How many milliliters of a 20 molar stock solution of KMNO4 do we need to make a, let's make one really, really, really dilute, just so you have a very big difference in the color here. A 0.05 molar oh. Okay. Okay. Yep, yeah, yep. Third, I have prep. Quarter of 10. Yeah. Okay. Thanks. Bye. All right. So we have a 20 molar stock solution of KMNO4. We want to make a 0.05 molar. So that's a humongous drop, right? So you know what? I'm going to be smart about this. Give me 1 second. I make these questions up as I go. If this number doesn't make sense, and then that's going to irritate me. So just give me 1 second. Let's do. Okay, that's a little too small. Let's make that, let's go, sorry about that. Better to check than, be safe than sorry, right? 1 point, let's go, no, 0.1. 0.1 for the molarity. Instead of 0.05, let's go 0.1. Okay. You ever hear the expression, measure twice, cut once? Measure 3 times, actually. You should. Especially if you ever own a house someday and you're doing housework, like I have, and I'm like, oh, I measured it right. Nope. 3 times. All right, back to this. So check your numbers is the moral of the story. 20 is our molarity. That's the little one here. We need to make a 0.1. That's a pretty big drop in concentration to make a 0.1 molar solution. That's an N. Solution with a volume of 250 milliliters. I'm ending this with a question mark. So let me rephrase it now and reread it now that we got everything down. How many milliliters of this? How many milliliters of this do we need to make a 0.1 molar stocks or a 0.1 molar solution with a volume of 250? So I want to fill this up to 250. I want to know how much of this do I need to put in here to make a dilution with a molarity of 0.1. Now you're sitting here and you're like, okay, this is kind of boring stuff. Maybe you think that, and I get it. But for me, I had to learn this a long time ago because I make solutions all the time for labs, or when I was in college I had to do this. This has to be easy. You don't need to do this. You're not going to have to do it on a test, like actually do it. But I think it's important to understand how to do it, right? Take chemistry, you should be able to make a solution if you need to. So this is how you do it. You just need some information. The concentration of what you start with, the concentration and volume of what you end with. So I gave you M1, this is M1, this is M2, and this is V2. So I gave you 1, 2, 3, you are looking for V1. So go ahead, use your calculator, set up the work, show the work, solve for V1. I'll give you a minute or so, a couple minutes. I'm gonna walk around and see how you're doing. And then I'll actually make the dilution, and then we'll move on. Your homework problems are similar to this. I'm just going to erase this so we have space. So again, show your work. So, you know, set up the equation, plug the numbers in. That's showing work. And then solve it. Don't forget units. And you know what? I didn't do a good job with the sig phase, but that's okay.
I have most of them done.
I've got 2 questions done.
Well,
I have one more.
where's it going to be?
I'm gonna do log 9.
Alright, Stu told me to go down and see your morning was Alright.
I'm not gonna stay after tomorrow
Yes.
for that.
Yeah, give me the answers.
Study for that.
Okay, still gotta show your work.
I'm gonna make flashcards for the formulas.
Laura, very concerned that I gave you guys the answers here on your homework. That's just so you can check. Not this Laura, that Laura. But maybe this one's concerned too. I still want to see work for this, right? So if you come in tomorrow and you just have the answers written down, that's not going to get you any credit. So make sure you show work. I'm glad you brought that up. Thanks, Laura. All right. Unit 1.25. What? 1.25 milliliters. Or, like I saw Marcy, she wrote it in liters, which would be 0.00125, right? Yes. So you could do liters if you want. But when we measure, we're going to use milliliters. But either one, it works. 20 times x equals 0.1 times 250. You can use liters for volume or milliliters. It doesn't matter as long as you are consistent. So this has to be milliliters if this is milliliters. This has to be liters if this is liters, as long as it's consistent. We divide by 20, divide by 20, right? So multiply and divide, x equals 1.25 milliliters. So here's my question. How many milliliters of water am I adding to this? If this is the 1.25 milliliters I need, how much water am I adding? I don't need to think about it because I just fill it to the line. But what if I asked you that? How many milliliters of water? Earl, can she see this? Here, over there. Is this in view here?
Yeah.
Sort of?
It's on the side, but yeah, you can see it.
Give me a little rotation there. You can just turn the top. Yeah, there you go. Good job, bro.
Thanks.
All right. Okay, so we're going to take 1.25 milliliters of this. So I'm going to reach in there, pull some of it out here. Now, because this is such a small amount, I'm going to teach you guys something here. This is not a very good way to do it because 1.25 is very hard to see and a lot of it will actually stick to the sides. So what you would want to use is a volumetric pipette, which I didn't get out because I just didn't have time to get it all out because you need a special thing. If I had time later, I'll show you what that looks like. If not, I'll show you tomorrow. But in real labs, chemists don't really do this. This is kind of like amateur hour. They have these bulbs that you put on a thin pipette. You just suck it up and then squirt it in, and it's very accurate. So this is not how you're supposed to do it, but for the sake of demonstration, I'm adding 1.25 milliliters. Okay, it's probably a little bit less because look how much is stuck in that graduated cylinder. So now, this is just tap water because it's a demonstration, but you would most definitely use distilled water if you were using this for something besides a demonstration. So now, what I'm going to do is pour in the water, and we'll fill it up to that line.
It's like juice.
pretty close to exactly on the line, but again, you would be more careful. You'd use a pipette to add the last couple drops, make sure the meniscus is right on that line, and that's how you make a dilution. You want to make sure it's nice and homogeneous, right? So you put the cap on, and never trust the cap. I've learned that the hard way a few times over the years. So what you would do is you would now just invert this a couple times, but if this isn't tight, then you get purple stuff all over the place, and it stains really well. So we'll just do this, just in case. So you do this a couple times, make sure it is nice and homogeneous, all dissolved, and that's it. You made a dilution. So here's your original stock solution. There's your dilution. You can see this is lighter, not a ton lighter, but it actually is significantly lighter. It's significantly less concentrated. This is 20 molar. This is a 0.1 molar. That's how you make a dilution. Okay? So that's how you make a dilution. I wanted to show you so you can have a visual. Sometimes we do these problems and it's like, okay, we just do it. We get the answer. We can learn the process. But I want you to see something once in a while, right? So that's how you do it. So, questions with the math or anything I did up here? Does this make you thirsty? Does it look delicious? Looks kind of good to me, no? Yeah, I mean, it would probably kill you, but, you know, and it would taste horrible. Oops. All right, so that's it for dilutions. Okay. I don't really have time to show you the video again, even though I'd like to. Maybe tomorrow. The very end of the video, they kept chanting, depends on concentration. Anyone remember that part? And then he spelled it wrong. I'll just show you. Lights, please. It's important that you learn this little jingle here. Depends on concentration. So we're not going to watch the whole thing. Just the end. I got it. I got it. By the way, my cool website, don't forget, this is here. Kids, I guarantee you don't look at it and forget about it. All the videos I ever show are on here. And there's some down here for AP Chem too. So there's a lot of, and then I have one for Science Lab. It's actually a latitude longitude song. You're ever bored, go ahead and watch it. It's fairly entertaining. Back to this now. Where are we? Wait. Yeah.
I want to watch the steel drum one again.
Yeah, that's pretty cool. Where are you? Solutions video. Here we go. You know, every time I'm not here, my speaker, I come back and my speakers are messed up. It makes me crazy seeing these. What's the best part? The beginning? Alright, here we go.
Assault us on the water in a fever today. The eyes broke apart in the usual way. They made it harder for the water to boil and freeze. So
Stop it. No
the
way.
freezing temperature is a few degrees. Believing it.
Why is that doing that? Who's a YouTube guru? Why is that happening?
If you put more so you can, then you need to solve. That is supersaturation situations involved.
I like that part.
Day, the eyes broke apart in the usual way. They made it harder for the water to boil and freeze. So the freezing temperature is a few degrees. Colligative properties. Concentration. Colligative properties. Concentration.
So you need to memorize that and just say that to yourself all throughout today. Okay, colligative properties depends on concentration. What does that mean? Right here. How much is dissolved? Lower concentration, higher concentration. The higher the concentration, the more the properties are affected. Boiling point and freezing point are the two we talk about.
Electrolytes have a greater effect on the melting and boiling point of the solution than non-electrolytes.
Okay, what does that mean? Electrolytes actually have a higher concentration than non-electrolytes. Here's why. If I put NaCl in water, I produce 2 particles. If I produce salt in, if I put sugar in water, I get 1 particle. Salt, because it dissociates, actually has a higher concentration than sugar, even if it's the same amount of both. That's what they're trying to explain there. We're going to talk more tomorrow.
More solute that's the salt got more effect. Solution's boiling point increases direct. The freezing point decreases, which is really nice. In the winter, salt on road to prevent the ice. Add a solute, boiling point goes up. Add a solute, freezing point goes down.
That also, add a solute, boiling point goes up. Add a solute, freezing point goes down. I want you to say that over and over and over all day. That's your homework besides the worksheet. Make sure you do it, Earl.
I'll do it.
I'll do it.
Okay. I will not be after school, I don't believe. I think I have a meeting or something, but don't forget the worksheet. Have a wonderful day.